Hello Randy, hello everyone. Sorry for the inconvenience, but if you're seeing this, then it's because my connection is slow and not allowing to share video as well as audio at the same time. So this presentation is for the round table. The solar analemma. In this presentation, I'll talk about the solar analemma in just 6 points. So the points are: 1. What is an analemma in general? Second, how to produce an image of the solar analemma in particular. 3. The solar analemma chart and what is it for. 4. Factors that governs the solar analemma. 5. How these factors work to produce the shape of the solar analemma. And 6. Just a little bit of glance at the math and trigonometry needed to plot solar analemma, and there will be no equations, just show the concept. So first, what's an analemma? And this is my own definition or my understanding of an analemma. It's not the official one like from Wikipedia whatsoever. So the analemma is time lapse of a celestial body along one cycle of its movement, like a month or a year, or one Earth year, overlaying one frame every 24 hours. So, like for example, the one on the left top, that's the lunar analemma, taken for a period of lunar month. Top right is Venus analemma, and I'm not quite sure if this is along one Earth year or Venus year. Now the two on the bottom is solar analemma, and the one on the left is nice and straight up, and as you see the one on the right is leaning a little bit, or leaning too much in fact. That depends on what time of the day you decided to start your solar analemma. So we need to study this a little bit, so we go to next point, is how to produce an image of the solar analemma. First, where to aim. You aim south, directly south, that if you're in the northern hemisphere. Second, what time to aim. It's the local solar noon of the day you're starting. And which day you're going to start, it's any of these 4 dates. Those 4 dates, they match in the local solar noon time for them, so you just aim south, and when the local solar noon comes, you start taking pictures of frame every 24 hours. What if you want to start, say, in October, not in any of these dates? You would still have to use the local solar noon of any of these dates in order to have a straight up analemma. Otherwise, if your time is shifted, you'll see it leaning to one side or the other. So, as you see here, here's the 4 dates: the June, April, and September, and December here. These 4 dates, they fall along the central line of the solar analemma. Just to guarantee that the whole shape is contained in the smallest area, left to right. Second, or next, the solar analemma chart and what is it for. Solar analemma chart is just the analemma overlaid over a scaled chart. It has vertical axis and horizontal axis. The vertical axis is the sun declination angle at maximum plus 23.5, and at least, or the bottom, is minus 23.5, and this means that the declination angle means the latitude line where the sun is perpendicular to. Now the horizontal axis is how much the sun swing across the west if you take your first image in any of these 4 dates that I mentioned. So for example, if you live on the equator, and now it's 15th of September, so 15th. So if you live on the equator and on the 15th of September, this location here, the sun declination will be +3. That means that the elevation angle of the sun at that date for you will be 90 minus 3. That's 87 degrees and pointing south. So that's what you can do. One thing you can do. The other thing is, if you know that on the 15th of June, uh, your local solar noon is 12 noon exactly, and it's 15th of September. All right. So at 12 noon, when you're looking south on the 15th of September, the sun would be here 1 degree earlier. Still didn't cross the south. 1 degree equals to 4 minutes. So you'll have to wait another 4 minutes. So the solar noon on 15th of September would be 12:04. So the solar analemma we can use for many things, determining the sun declination angle, determining the local solar noon, and using the above information to conclude lapse long position, but with a Greenwich solar noon instead of your local solar noon. Okay, next. The factors that govern the solar analemma. As I showed before, the solar analemma has a vertical axis and horizontal axis. And the vertical axis is controlled by the declination angle of the sun, or it shows the declination angle of the sun. And the horizontal axis is affected by two factors, in fact, orbit eccentricity and axial tilt. So this chart here shows the analemma without axial tilt, and here the analemma without orbit eccentricity. When you add this one to this one, you get the one on the left. But how? Well, for example, if you check this date in the green circle, I think it's the what? 1st of February. They both on the same side, so they add to each other. But if you go here, that's the 15th of August on the right side, 15th of August here on the left side. They subtract from each other, and so it gets smaller like this. Next, how the factors work to produce the unique shape of the analemma. But before I start this, I should demonstrate a couple of points. First thing is the sidereal and solar noon. Sidereal day is the time that takes the Earth, or point on the Earth, to spin and then face the same point in space again, not the sun. And that's like at 360 degrees and takes 23 hours and 56 minutes. So the Earth is now here after 23 hours and 56 minutes, pointing at a direction that's not the sun, so this is not a solar day. A solar day is when the same point is looking to the sun again. So this here, it covered almost 1 degree, so we need to look 1 degree to the left side, so we add another 4 minutes in order this roughly 1 degree to be completed. And this is important, and you'll see why. The next thing is orbit eccentricity. This circle here is an ellipse, 583 pixel by 584 pixels. Its eccentricity is 0.058. That's more elliptical than the Earth's orbit. Just because to put things in perspective, because I'm going to show really elliptical ellipse to demonstrate the points. So how the orbit eccentricity affects the analemma to get with this shape without the axial tilt. So from position 1 here, let's say you're in London, you're facing the sun, so that's good. Now say after 20 days, the direction you're facing is not the same. It shifted 20 degrees to the left, like here in, but the Earth in this area is so close to the sun, so it goes faster. That's why the relative position of the sun changed very rapidly, comparing to this 1 degree per day, almost 1 degree per day. But then, between position 2 and 3, the Earth starts to slow down in its orbit, and so the angle of the sun, or the position of the sun, start to catch up with the direction that London is facing, or Greenwich, whatever the point we selected in point 1. Now, after that, the Earth keeps slowing down to the extent that the Earth rotation takes over and is faster than the change in the position of the sun. So you see here, your direction was facing exactly the sun. So maybe it's like here, and then after that, the sun became to the left, and then again on third position they match on the center together, and then on position 4 it reached the extreme, maybe to the right side, as is here. This is the right side comparing to your this is your south if you're looking south in the northern hemisphere. So that's how the analemma happens without axial tilt. Now the second thing is axial tilt. How the axial tilt gives this figure of 8, a perfect figure of 8 without the eccentricity. So to start, I'll presume a circular orbit and no axial tilt. As you see here, there's two disks on top of each other, the subsolar path and the equator. Actually, I'm interested just in the outer rim of these disks. So the direction of the sun, or right here, this would be the subsolar point moving across the subsolar path along 1 year. From this starting point, if we have the certain longitude line, call it X longitude line, experiencing a solar noon, after a few days it will look like this. They moved an equal amount of degrees on their both planes, and both planes are on the same plane, so no problem, they catching up with each other. But if we give a little bit of tilt like this, now we're looking on top view from, say, the polar star, looking on top of the Earth, and the orbital plane, the orbital plane or the ecliptic is tilted across the plane of the equator. And you see, there's a horizontal shift that happened here. Not only horizontal shift, there's also vertical shift, which is the declination. So next, I'm just here showing the angle. So how this makes the figure of 8? Here is an exaggeration just to make things clear. They both started together at, say, the equinox, for example. So both of them was here, but then the sun became slower. So let's say that it's moved to the right side, or let's just take the relative position here. The sun is to the left, so the sun began moving to the left relative to my position. But then when they both travel 90 degrees in their respective planes, they match up again. So this is what happens here. And when they start moving from this point to that point, then the direction of the sun will be faster, will be ahead of the longitude that we picked. So the direction will be to the right of the observer, and then they match up again on this in the next equinox, and the cycle goes on. That's the figure of 8. Now the next one is a glance at the math and trigonometry needed to plot the solar analemma. So the first step if you want to build a sun calculator or plot Analemma or do anything related to the sun, is to know where's the Earth's position in relation to the sun. And to do that, you start with the perigee to do all your orbital mechanics based on that point, and that point is usually on the 3rd of January. Now, after that, you take a reference point because you want to know how far the subsolar point traveled on the plane of ecliptic. So here's this is the point of equinox. We take note what's the longitude line that experienced the equinox, because the equinox is just a moment, technically is a moment. And then through orbital mechanics you calculate how far this direction of the sun traveled along the plane of the ecliptic. So next, alright, so what do we do with that? Calculating how far the subsolar point traveled from a reference point along the plane of ecliptic. Um, for a certain period, you know how far the longitude traveled because the Earth's rotation speed is fixed at almost 1 degree per day, and you can of course you should use the very accurate number if you wanna do an Analemma or sun calculator. Uh, so we have this angle here. We already got it from our orbital mechanics. Now we start to project some triangles and solve them. So for this triangle here, we have the angle, we have this r, just any arbitrary number, and if we get this r, then we have u, and we have the y, and we have the x. So why do we need this? Because we will project the x on the equatorial plane, like so. So this is the x, and this is the projected x, or x after the tilt. The tilt is 23.44 degrees. So now we have the hypotenuse, an angle, and this is the right angle. So we can conclude the projected x. And what do we do with that? We do this. Looking from top view on the equatorial plane, we have the x with the tilt, and we have the y. So now we know this angle. This angle is not the same that we concluded from orbital mechanics because we're looking at from a different direction. This is what we want. How much the sun shifted from the longitude line when they were together at a certain point. Now the next one, I'd like to show something before we proceed. So now we're going to calculate the declination angle and the sun shift at the same time. We already got the sun shift, so but we can see it here again. So we have the projected x, and we have the original x. So now this is another triangle with a z as a vertical elevation that connects from the equatorial plane to the plane of the ecliptic. So now we have other triangles that we have more information about. We have the information about the r. We know the r is just arbitrary value that we decided to make, and we have the z. So and the z of course is vertical, so this angle here between the orange and the z is 90 degrees. So we can get this angle between the r and the projected r, which is the declination or the elevation angle of the sun upon the equatorial plane, aka the declination angle of the sun. So through this diagram we have the declination angle of the sun and the shift of the, the sun direction relative to that longitude line. And that's all.